All right. So anything in Appendix F that you would want to look at. Now, on 23 through 34, that's essentially unit circle stuff. Okay, and there, like I said, there's a unit circle that I posted online on our website. If you don't know how to get to our website, be sure to come talk to me so I can show you. But it's just on School Fusion on CarneyCats.com. Go to my class page, and there's a link right there. Under Documents, there's a bunch of documents listed by chapter, and in Chapter 1, there's a unit circle PDF. You can print that, look at it, help to memorize it, that kind of stuff. So 23 through 34 is just that. Stuff. So any others? Yes, Shelby. In 17 through 22. All of them? Mm-hmm. Sure. Once you get a few of them, though, you kind of start getting the hang of it, I think, here. Basically what this is just reviewing a couple things we did with odd and even, and then some kind of essential trig identities. If you but just look on the previous page, the A46 page at the top, there are a few trig identities right there on the facing page. Sine squared plus cosine squared equals 1 being a really important one. The other ones aren't really that big of a deal, to be honest with you. If we ever need those, we'll look them up or I'll give them to you kind of thing. All right, so they were given to you right over there. So if you didn't think to look there, then that is maybe part of the problem. So quickly on 17, it says sine of negative a. Well, what I would want you to do there is remember, hey, sine is an odd function, right? So sine of negative a is equal to what? Odd function means opposites in, opposites out kind of thing. So sine negative a, another way, right? That's what? Negative sine of a, right? If I put the opposite in, meaning a, I get the opposite out, which means negative sine. Okay, well, what's sine of a? B. So this is just negative b. They wanted the answers to be in terms of numbers and b's only. So that's why you would write that, okay? But I'm glad you asked about it because it's not enough to just look in the back. It's an odd problem, get the answer, and think, okay. You got to understand what's happened. So the same thing would be true, well, we just did 18 then, didn't we? Right? Look at 18. That's negative sine A. Oh, that's negative B. So that was even easier. Cosine negative C. Since it's an odd function, what's cosine negative C equal? Or excuse me, an even function. It's equal to cosine C. Now what's cosine C? 0.3. So your answers are supposed to be either numbers or B's or some combination of numbers and B's. Okay? Then we get to sine. I'm going to skip here a second to sine squared A. What does sine squared A mean? Well, what that really means is sine of A squared. Now, I don't know how many times in this class I will lament the fact that we use this shortcut notation because it causes us all kinds of problems in calculus. Okay? It's great when you're in trig, and it's nice shortcut to write, but it's brutally confusing in some calculus things we do. You've got to remember when you see sine squared A that it really means this. Because we'll be dealing with functions and we'll need to know what's the outside function, what's the inside function, and people get all confused with this. Okay? This is what it means. Okay, well, what's sine of A here? In this problem, what's sine of A? B. So what's this equal to? B squared. Okay? And then sine of 2A, we would look at the other page, and we would see that sine of 2A is equal to 2 sine of A cosine of A. Right? Now, sine A is equal to B, but what's cosine of A? Well, I don't know. Well, here's how you do 20 as well as the rest here of 22. The way we would get cosine of A is we would say cosine squared A. I'll use it, as unfortunate as this lingo is. We're used to using it, so I'll use it. Cosine of squared A is this, or cosine squared A is this. What did we just say sine squared A is? B squared. So I'm going to subtract a B squared from both sides. Then I'm going to do the square root of both sides. cosine of A is equal to plus or minus the square root of 1 minus B squared. So I will substitute that right there and get plus minus square root of 1 minus B squared. And now I have an answer that's in terms of numbers and B's only. Okay? So it's just some work with these, and that's the same thing you do on number 20 to get sine C. You know cosine C. So set up cosine squared C plus sine squared C equals 1. Put in your 0.3, and away you go. All right? So, Cody, did that answer what your question was?
Yeah.
Okay. All right, let's move to Appendix A. Appendix A is the thing that we really want to deal with here today. This does kind of get into something we're going to get into tomorrow more so. Now I have to leave a little bit early tomorrow, so we'll get through what we can. It's a little shorter lesson tomorrow anyway, although there's a part of it that there will probably be a fair amount of time spent going over today's homework, I'm thinking. So I will take a video of second block tomorrow if you find that helpful to, need to look at some things tomorrow. But we'll get through what we can, then you'll probably have a little more work time. So I'm going to try to get a little of the ideas across today as well. So you understand kind of what's happening. And this thing we had to do, I want to get a presenter here. So let's find one here. Dakota, have you been the presenter? Okay, that's okay, you're going to do it. All right, luck of the draw. So, go to your scratch pad here. All right, and he's got some stuff in there from some of the homework, it looks like. Let's go ahead and get those out of there. And were there any questions on 14, that section with the roots, finding the roots? Everybody okay with that? Remember, you essentially trace, right? You go and you trace, and it'll pretty much tell you the root, where the root is. Also, you can go to menu, go under menu real quick here, Dakota, and then analyze graph, and then 0. The 0 of the function is the same as the root, but go ahead and escape out of there. We won't worry about that now, but you can find the roots, find where it crosses the x-axis. Now, there will come a time where we're interested in that, but to be honest, most of the time to find the roots, we'll actually just solve the equation. I mean, think about it here. If I've got this, I guess I'm on the video here. If I've got this, what was it, number 14? Number 14 said f of x equals x minus 2 plus 2 cosine x. If I'm looking for the roots, what am I looking for? Where what equals 0? The output, right? So I want to know when that equation is equal to 0. So really I need to solve that equation. Now that's a hard equation to solve. We did some work with trig equations, but not trig equations that had other x's in them, right? I mean, that's not one. There's really no algebraic way to solve this. We did some factoring, remember, on that one worksheet with the trig worksheet and stuff. But there's no good way to solve this. So electronically is really the best way. So one way was to graph it like you did on 14 and find where those roots were. And there's like 3 of them, I think, right? Dakota, go ahead and put this one into your calculator. There is something I did want to show everybody now that I say this. So you might, if you want to, go ahead and put 14 into your grapher screen. If you can just watch up here if you want, but you can put it into yours. But we could just solve this equation. And one of the reasons, this is one of the big ones, one of the big reasons that I wanted you to get the CAS version of the calculator here is it will solve this equation. The non-CAS version will not. Okay, CAS stands for Computer Algebra System, and it will do the algebra that we want it to do here. So anyway, if we go back to the calculator, so Dakota's got it graphed. Now, I'm not sure what kind of window he has here, kind of a standard negative 10 to 10 kind of thing. Here's what I wanted to show you. The directions said you were going to look at this graph from negative 5 to 5, and in calculus this happens a lot. Here's a function, look at it in this window, this domain. So let's go to the window. Let's go to the window settings. Let's go to, and actually he's got a pretty nice window. You can see the graph, but sometimes when your window comes up, you can't see the graph. You can't hardly see any of it, or maybe just little pieces of it. So this is a really cool thing. Hit -5 and 5 for your X, min, and max, and then just hit OK, or you can hit enter at this point. It's got a little heavier box around it. That means you can hit enter, and it'll just do that. Okay, now he's got -5 to 5. Now he's got a pretty good window. Now there is some extra empty space, but sometimes you'd be in a window where you can't see it all. So what Y should you set? Well, you can set it manually. But if we go back to window and go to menu, window, zoom, and go down to A here, zoom fit. And what zoom fit does is it will take your X, min, and max that you've already put in. So to use zoom fit, you have to first put in an X, min, and max, okay? It'll take those X's and it'll figure out all the Y's, and it'll set your Y window automatically so you can see them all. Now, it doesn't work real well when you get one that's going up to infinity or something like that. Then you get too big a window and you can't really see. But a lot of the time, it's a pretty good idea. So put in your X, min, and max, and then do a zoom fit. It's a pretty cool thing. All right, so there's 1, 2, 3, 0. So you can trace, and you can do those kind of things and find them. But you can only find one at a time. So it takes a little while. So go to your scratch pad, hit your scratch pad key to go to your calculator. Now let's do this. Go to menu and to algebra and then to solve. And now let's type in this function. X minus 2 plus 2 cosine X equals 0. So you got to get out of that parenthesis there, right there. No, stay inside that. Yeah, in between the two parentheses. Equals 0, comma X. So we're telling it to solve that equation for X. And look at that. Now, are some of you getting more decimal places than that? Yeah. You're only getting 6. Go to, I thought we had set this the other day, but maybe not. Go to Doc and Settings and Document Settings. And we want this to say plain old float instead of float 6. Okay, plain old float, which will show us more decimal places. Okay, hit enter. Apply this setting, okay. All right, now go up, arrow up and grab that again. Hit enter, and then bring it down. Now hit enter again. And now you get more decimal places. Okay, so I think that's a good setting to have. We changed that somewhere the other day, and
It was just over a bunch of
maybe. Well, I thought we did. But we were in the graph screen. Hit tab, hit your scratch pad again, not tab, but hit your scratch pad again. And now let's go into menu. Let's go into menu this time in settings. And I think that might be where we set it. Yeah, and that one we want to be plain float. So there's a couple different places where that happens. So I think maybe now we might have it set right everywhere. So you just can see more decimal places. Okay, but there's all three of them, boom, just like that. So most of the time, if we want roots, we'll do it as an equation. It's pretty cool. I mean, because that's just one that there's not a simple algebra way to do it. Now, if you go to a college calculus class and they won't let you use one of these, which is possible. I mean, different professors do different things. Well, what it means is they won't ever give you a function like this. They'll have to give you one that you can factor or do trig with or whatever, which is fine. But the real world doesn't work that way. I mean, they don't all come out pi 6. You know what I mean? And sometimes you have to use technology to figure these things. So anyway, but that's my. But we'll that's something we'll kind of do. So let's move on to number 20. What do we have? 25 and 29. Let's just do 25. They're essentially the same thing. So let's graph cosine x. So let's go back into our graph screen so we can get rid of that one and just graph plain old cosine x. Okay, and the directions were kind of strange here. The directions said, graphs of most calculus functions look straight at small scale. Now, so and this is what we're going to really, tomorrow's homework is really about, not today's, but tomorrow, is this idea of zooming in. And I explained it to a few of you yesterday, but this is curved, and we're going to talk today about slope of the curve. We've already done that a little bit in those explorations, so hopefully you have a little bit of sense of this. But we're going to be talking about the slope of this thing. Well, all we know at this point is slope of a line. How in the world do you do slope of a curve? We do 2 points on a line, that's slope. How do you do slope on a curve? Well, what we're going to do is we're going to say, if you looked at just a teeny tiny piece of this curve, it would look straight. Does that make sense? I mean, if you just looked at a teeny piece of it, it would look kind of straight. So what they're saying here is find a window centered at the point 0, 1, so right here, where this graph looks straight. Okay? In other words, zoom in, like put it under a microscope and until that looks straight. So here's what you do. You go to menu, and there'll be a lot of ways to do it, but a quick way here, go to window zoom, go to zoom in, hit enter one time. Now you get this little glass, okay, you might need it again, but that's okay. You got this little magnifying glass with a plus in there and asks you for the center. So you use your trackpad to put that right on the point 0, 1, or real close. So you just kind of move it with your finger a little bit. You got to, don't hit enter though, or don't, get up here, come on, come on. No, up 0, 1. This one. All right. DC volunteered and everything. I shouldn't beat on. All right. No, I guess he didn't volunteer. Okay, hit it. Now hit enter. Hit the middle of the trackpad. Okay, and it zooms in and it sticks it in the middle of your window now, right? And does it look straight? No. And you can kind of tell we're zooming in though, right? And now do it again. Hit enter again, or hit the middle of the trackpad, and then you might have to move the magnifying glass a little bit. Hit enter again. Doesn't look straight. Doesn't quite look straight. Try it again. And people always ask me, well, how far should I go? I would say go until it looks straight and then hit it one more time. Okay, so you say, yeah, that looks pretty straight, so we'll hit it one more time. Okay, so now, it looks straight, but imagine where we are, right? We're at the top of this hill. It was coming up like this, and it was curved, but right there, we're just in that tiny little spot. Matter of fact, if we trace, let's go to menu and trace, graph trace. Now his is right at the point 0, 1. Is everybody's? Okay, if it's not, you can hit a 0 and hit enter right now. And that'll put that right, you're right kind of in the middle. All right, now type in 0.001. Okay, so you can see how zoomed in we are, right? Because 0.001 is a little ways over there. I mean, so we're really, I mean, the far edge of the screen is what, like 0.09 or something, or something like that. So we're really zoomed in. So the idea is going to be with slope anyway, is going to be, if we took 2 points on the curve here, even though it's not a line, if we took 2 points and did that slope, wouldn't that be pretty close to the slope of the line that would be there? And the answer is yes, obviously. But that's what that's the kind of thing we're going to be talking about. So being able to zoom in and trace along a graph like this and pick some points, that's something we're going to be doing in tomorrow's homework. Okay. So that, and then the question said, find a window. So at this point, you just go to menu, window settings, and you would just put in, okay, negative 0.02045 to 0.0186, and the Y window 0.9755 to 1.0269. I mean, just give a bracket, your X range, your Y range, and that's that's all they want. That's really all they want is that window. Okay? All right. So that's what 24, 29, or 25, 29, those were about. All right, let's go to the document that you had up here. So how's the quickest way to get to that? Home button, probably. Home. Number 4 here is your current. I'll tell you what, let's go back to home. I changed my mind. I want to go to my documents. And you guys don't have to, but I just want to show you something real quick. Let's go to that local linearity, the one I gave you there. Do you want to save changes? Yes, no, it doesn't matter. I haven't really done anything to it. I hope. Okay, local linearity. So if we hit Control and right arrow, Okay, and here's a function that they've already put in for us, so we could change that if we wanted to. We could just type define f of x and put in a new function if we want to, but I don't want to right now. So let's hit control right arrow. And okay, so here's the function on the left, and what they're saying is that the same thing we were just talking about, that if we zoom in, and so you can hit this little down triangle here, okay? Now don't hit it too many times or then it gets ahead of where the calculator can go. So just hit it 2 or 3 times. And then watch what's happening in the yellow. We're zooming in, okay? It takes a little while, especially since we're hooked up to being the presenter, so it takes a little longer. And eventually, as he goes, try to just hold it down. Click and hold down and see what happens there. I think that's sometimes better than clicking a whole bunch of times. Okay, we're zooming in, and it's taking a little while because we got this part over here. But you can see what's happening. We're zooming in, and at some point, we're going to be able, this thing's going to be pretty much just straight. Okay? And then the idea is, once we're zoomed in far enough on that little piece of it, okay, that's good enough. We can now take 2 points on that curve. Remember, when we're talking about the slope on a curve, which we're going to get into in a second here, we're talking about the tangent line. And the tangent line only touches the curve at one place. So when you take 2 points on a curve and do the slope, you're not really doing the slope of the curve. Okay? You need to do the slope of the tangent line. There's only 1 point on the curve. So that's why we need to zoom in. So but again, we'll work on that over the next several days. So, all right. So good enough with that for right now. So we're going to take a few notes. So let's switch to our book, page 35. And we'll come back to the calculators here in a little bit. So we'll let somebody else present at that point and let Dakota off the hook. But you did a fine job, I must say. I am, yeah. Page 35, section 4. Now, well, actually, there's only a little bit on 35, and it goes on to 36. So, I want to welcome everybody to calculus, by the way. Because, yes, welcome. Because we're now ready to start calculus. Quite honestly, other than those exploration stuff, we really haven't done any calculus yet, right? I should mention the quizzes. We totally did not mention it. Have a few people still have to make those up. They are graded. You maybe have seen that they're on Power School. If you want to come in and ask me about them or something, you can. But we will go over them in class here in a day or two as soon as they get the people that were gone get them made up. Okay. The first quiz is not necessarily representative of how the rest of the year will go. Okay. I've had many instances of people not do so good early. And remember, that wasn't even calculus, right? Now, it's function notation and stuff like that will be important, but heck, the calculus stuff might go easy for you, right? And maybe you struggle on some of those things. There were a couple questions on there where if you got off track, you might have lost 3, 4, 5 points, and out of 29, that's quite a few points. So, in the big picture things, you definitely have a chance to recover from that. I've also had people go the other way, not to rain on your parade, but I've had some people do really well, and then all of a sudden, I don't know, get a big head or something and think they didn't need to study anymore and go on. Now, if you didn't do as well, though, as you would have liked. There is an old saying, the definition of insanity is to keep doing the same thing over and over and expect different results, right? I mean, you may have to change some things, some study habits, or coming in and asking questions. I haven't had a lot of people coming in before school or lunchtime necessarily. I think about the one with I talked about the one with the circle and the piecewise function, right? I told you that was going to be on. We did one in class. You had one for homework. We did another one when we reviewed. And there was people missed out. And to me, that one seemed strange because 3 different examples, told you it was going to be on there. So if you missed it, somehow that I would guess the 3 examples we did before you didn't understand or didn't get it. You should have been in talking to me about it, right? Because you knew it was going to be on. So that one was a little hard to understand. So that would be an example of something you could change to improve next time, okay? But there were some of them that, well, I didn't get that one, but I'll do better next time, and, just keep doing my homework and do the best I can. So overall, I thought the results were good. Overall, I think the average was reasonably good compared to previous years, right in the ballpark, if not maybe a little better than a lot of years. So overall, I'm pleased with how we did so far. But today we are going to start with the idea of the derivative. The derivative. Okay? Now, you know what? This is going to look better this way. All right. So, the derivative is this. This would be one way to think of the derivative. The instantaneous rate of change, so you can think back to those explorations that we did, of f of x. The instantaneous rate of change of a function. Another way to think of the derivative is the slopes of f of x. Those two are interchangeable. If we are working on a story problem that deals with rates, for example, miles per hour, degrees per second, like the door closing, maybe we're selling textbooks and our rate is our profit per book, dollars per book, those are all rates, okay? Velocity is a rate that we work with a lot because it's just a very easy one to understand, and we're all familiar with the idea of velocity, so that's the rate we talk about a lot. Then you would think of it as an instantaneous rate of change. But if we're just dealing with a math function of just some graph that has no units or context to it, then we would think in terms of slopes. Okay? Now, the label we use for the derivative is this, and we read that as f prime. F prime. That little mark is read as prime. F prime of x. Sometimes we don't even put the parentheses x. Sometimes we just write f prime like this. Okay, it doesn't matter if our input is x or t or whatever, it doesn't matter. Okay? That is the derivative. F prime of x is the derivative of f of x. A derivative always has to be associated with an original function. So, when I write this, okay, f of x would be our original function. What we might call our amount function. In other words, the outputs of it are some amount. For example, miles. If we have a position function, it would be miles. That's the amount of miles we've traveled. The degree function in that exploration when the door was opening is the output was the amount of degrees the door was open. Right? Elevator in a rocket was the miles, I think it was miles, that she had traveled in the rocket. So we call that an amount function. F prime of x then could be thought of as the derivative of f of x, could be thought of as the rates of f of x, could be thought of as the slopes of f of x. Those are all the same thing, but they're all associated with f of x. Okay? Now, let's go to the other document I sent you, the derivative grapher document. And Cody is the presenter this time. Okay, so just go to the home screen would be the fastest. I would say don't save it this time. I would say there's no need to save what we had. So go to derivative grapher. I would say no. on the changes, just so it won't take as long. It's been a good day today. Mr. Gans came in to do a little walkthrough and watch me, and we were doing this, and he was just couldn't believe that we had somebody's calculator up on the screen here showing. In fact, that was pretty cool. So I think I scored major points today. All right, so let's control right arrow to the next graph. Okay, all right, and what we have here is a red graph that is f of x, and the blue graph is f prime of x. Okay? The red graph is f of x, and the blue graph is f prime of x. Okay, go ahead and go to the next page. Okay? Trace y equals with the slope of the tangent line. So go ahead and go one more page. All right, and what we see on this page is we see the blue tangent line that's on the red graph, right? Everybody see that? Now, so what I was talking about earlier, this is key. When we talk about the slope of a curve, we're talking about, what we're really saying is the slope of the tangent line at a certain point. So when we talk about this, I probably should have written this down here. So let's go back to that. We probably should have mentioned here on these slopes, we're talking about the slope of the tangent line. Because slope only makes sense. Slope really only makes sense when you're talking about a line. Okay, it's rise over run. So when we're talking about slope of a curve, what we're really saying is slope of the tangent line on the curve. And remember, a tangent line only touches a curve in that one place. So now, think ahead to tomorrow a little bit when we're doing that zooming in thing that we just showed you a little bit ago. We want the slope of that line. We need 2 points on that line. The only point on that line we know is what? The tangent point, right? Because we know the function. We know the red function. So we can plug in, where are we at, 3.12? We can plug in a 3.12 into the function, and we can get this point right here. But I don't know any of the points on that blue line, except that one. So how do I do the slope? I need 2 points that are on that line. Well, if we zoom way in and look at this little piece right here, aren't the points on the red curve almost the same as the points on the blue line? You buy that? Right? The points right around here that are on the red curve are really close to points that are on the blue line. So if we would do a slope calculation with 2 points on the red curve right close by, it would be almost identical to 2 points being on the blue line. Okay, that's the whole point, and that's called local linearity. When you get in really close in a small space, the word local, it makes a line, local linearity. Okay, and that's how we're going to calculate eventually these slopes. Okay, but for right now, we just want to talk about it being positive slopes or negative slopes, stuff like that. All right, so here's a key component of the derivative. We said right here that the derivative is the slopes of f of x. What I mean by that is the outputs are the slopes of f of x. When I say that f prime is the slopes of f of x, I'm saying the y values of f prime are the slopes of f of x. So let's look at this. This 3.12 is the slope of the red graph. That is the y value down here. Make sense? Now, and who's our presenter? Cody? Okay. Hit this top triangle here, and that's going to move us. Now, don't hit it a whole bunch of times. Just hit it once or twice. As we move, okay. Oh wait. Hit the down triangle. I told you wrong. We want to move to the right. Okay. As I move that line to the right, hit it a few more times. Now it's moving left. Okay, hit the top one again. I thought it was moving the wrong way last time. Okay, I was wrong. I was actually right. I was wrong when I thought I wasn't right. See, I should know better than to think I wasn't right. What was I thinking? Okay, hit the, that's what I need to do. All right, so as this point moves to the right, what's happening to the blue line? Its slope, yeah, it's the slope is getting less. Now it's still positive, but it's getting less positive. Could I use that term? Less positive, right? 5, 4, 3, 2, right? That kind of thing. What are these y values doing? Positive and getting less positive, aren't they? Do you see how this blue slope is corresponding to these y values? Because now when we get up here to the peak, go ahead and keep going. When we get to the peak here, what's our slope? 0. What's our y value down here? 0, right? All right. So the slopes, and I don't, if you want to write this in your notes, I suppose you could, right? F prime is, how do you want to say it? F prime is a plotting of the slopes of F. F prime's y values, F prime's outputs are the slopes of the F function, right? I mean, that's what we're saying here. F prime's outputs are the slopes of the F function. Okay? So there he is. He's got a slope of 0, and that corresponds to this. Okay? So go ahead, Cody. Just, I know it's tough. Go ahead. Get it written down. It's tough to write notes and be the presenter. So go ahead and hold down. I think you can hold down. Just hit that top triangle and just hold it. And then we won't run out of, okay? So now as we're going, the blue, now the slopes are negative, right? And would you say getting more negative? Does that make sense? Like you're getting slopes of -1, -2, -3, getting steeper. Okay, stop. Go ahead and let up. So what's happening down here? The y values are negative and more negative, right? See, to me, decreasing gets confusing. We've got to really be careful with that. And again, your head's going to start spinning with some of this stuff at some point along the way here, right? Over the next 3 or 4 days, we're going to flesh this all out. And your head's going to spin for a while thinking of all these connections, and that's okay. You really need to go through that process of thinking about, okay, when this happens and this means this, and then, and by the end of 4 days, we'll organize all this kind of into a nice chart format that we can really kind of memorize and make sense of and stuff, okay? But for now, it's going to seem like a lot of stuff. But decreasing, what's decreasing? Well, numbers can decrease in 2 ways. Positive numbers decrease by going 5, 4, 3, 2, 1, right? The numbers get smaller. But negative numbers decrease the other way, right? -1, -2, -3, -4 is decreasing, right? So I like to say decreasing is positive and get less positive, or negative and get more negative. I would probably get kicked out of the math teacher club for doing that because that's not really a technically good way to say things, I don't think. But I don't think so. And if I get kicked out, I guess I don't care. But positive and getting less positive, and negative and getting more negative, right? Probably don't get kicked out or something. But all right. So anyway, right? So what's happening right now is our slopes are negative and getting more negative. But then what happens right here at the inflection point? Isn't that an inflection point here? Concavity's changing. What happens here? Now, the slopes are still negative, right? But they're getting, I mean, if this was, what's this slope? -2, okay? Now the slopes are going more like -2, -1. Go ahead and go to the right. -2, -1. I would call that negative and getting less negative, right? That's actually increasing, isn't it? Negative and getting less negative is actually increasing. And sure enough, look what these slopes are doing. They're negative but going up towards 0. Okay, so go ahead and keep going. Just hold that down. Yeah. And of course, the slopes get back to 0. And then here, what's happened? The slopes are positive and get steeper, which would be positive and more positive. And sure enough, these y values are positive and get more positive. All right. So, and somebody had asked the other day, I don't know if it was in this class or the other class, about how are derivatives always like parabolas. No, that's just some examples we a lot of times use in the beginning, but they're not. The derivatives look different depending on what the original function is. Okay? All right, so a big part of today is just understanding this connection between an original function f and its derivative f prime. Slopes is how we often think about it. Okay, now let's move to our book. Thank you, Cody. Let's go to our book now and look at page 37. And let's see. I apologize to, let's see, are we missing? Who are we missing? Bailey? Hayden? Okay, sorry if you guys are watching the video because you're not going to get to see this part right now. But we're on page 37. And I want to look at those two graphs right here. Now this is a lot like the balloon example we looked at earlier. If you read back at the bottom of page 36, this is a picture of a car leaving Bismarck, North Dakota at noon. And this function P is the position function. So this is, at least they can see what I'm going to write here. Okay. So this function, the graph on the left is P of t, which is going to be position east of Bismarck. Okay? So that means if it's positive output, it's east of Bismarck, and if it's negative output, it's west. Position can be both positive or negative. Now, distance is usually just positive, but position can be positive or negative. It has direction in it. The second graph is the velocity of the car, the eastward velocity of the car, and that's going to be v of t. Okay? So we have v is the eastward velocity. Now, so if it's positive, it means the car's what? Moving east. And if it's negative, moving west. So if you look at a map, east is to the right, west is to the left, so positive right, negative left, that makes sense. All right. It is not a coincidence that I wrote these two functions where I wrote them. What is the velocity function? The slopes, the rate of change of this one. So another way to write the velocity function would be P prime, right? It's the derivative of P. It's the slopes, it's the instantaneous rate of change of the position. So P prime and V would be equivalent ways to talk about these two functions. Okay? Now, one of the things that you will be asked in your homework today is, and I know this will be on our next quiz, will be to look at some function notation, be given a description of the problem, and be able to say what it means in terms of the problem. So if I told you that P of 2 equaled 70, what would that mean? 2 hours after noon, or at 2 p.m., right? Now, somebody in the other class, the first answer I got in the other class said after 2 hours, or at 2 hours, they were 70 miles east of Bismarck. And I said we can do better than that, and I'm glad you referenced noon, because they did tell us it was the time since noon. So a good answer would be what you said, or just say 2 p.m. At 2 p.m., at that instant, that's what makes it instantaneous rate of change. At 2 p.m., the car was 70 miles east of Bismarck. Now, do we know what direction it's going? From that information alone? We have no idea. It could be stalled on the side of the road. It could be going east. It could be going west. We don't know. But at 2 o'clock, it is 70 miles east of Bismarck. That's its position. Now, if I said that the velocity, if I said v of 2 is 100, then what's that tell me? At 2 o'clock, it's speeding. Unless North Dakota has some speed limits we don't know about. It's going 100 miles an hour in an eastward direction at 2 o'clock. So it's 70 miles east, heading east at 100 miles an hour. If this was negative, it's coming back towards Bismarck, right? West. It's heading west. So it's 70 miles east, but it's headed west at 100 miles an hour. Now, I can pretty much promise you on the quiz, though, I'm not going to ask it as v of 2. I'm going to show it as p prime of 2, right? But those are the same thing. P prime is the derivative, the rate of change of p. So if p is in miles, then p prime's got to be miles per hour. It's got to be a rate, right? It's the rate of change of p. Okay, so these two say exactly the same thing. And we got to get used to that notation, what that is mean. Okay, it's the rate of change or the slope. It could be slope, but remember what I said. If we're dealing with that calculator thing we had, which was just some function with no units or anything, we thought of slopes. If it's a problem like this that has units to it, then we might think rate of change or speed or velocity or whatever. Okay? All right. So let's take a little closer look then at this graph. All right, so let's focus on the position graph first. So it starts down here, which tells me what about the car? It's not moving. No? Yeah, there is movement in this, but that tells you its position. So it starts at Bismarck. And it goes up, which means since it started at 0, now going up alone doesn't tell me about where it is. Let me ask it this way. The fact that this graph is above the x-axis, what does that tell me? Now, careful. I heard some people saying it's going east. Think about what I said. The fact that the graph's above the x-axis tells us it's located east of Bismarck, right? Not that it's going east. When in this graph is it going east? From 0 to when? 3, right? At 3, it stops going east and turns around and comes back west. But at what point? At what times is the car east of Bismarck? 0 to 6, right? The car is east of Bismarck from 0 to 6. From 0 to 3, it was going away, going east, and then from 3 to 6, it was coming back to the west. See those different questions? Now, it has to do with the slope, doesn't it? Because it has to do with the direction. The slopes here are all positive. And sure enough, look at this graph until 3. The y values are positive. Remember what we said earlier? The slopes of this graph are the y values of this graph, right? So, these slopes are all positive, so these y values are all positive. These slopes are all negative all the way down to here. Right? Slope negative means it's going down. These y values are all negative all the way to there, between 6 and 7. Then the slopes turn back to positive for a little while, and then these y values turn back to positive for a little while. Okay? So I wanted you to see that connection, but in this one they have meaning as far as some direction. Okay? All right. Now, what about when this graph's going up and down? What about this? What do you know about the speed of the graph when this is going up and down, and the velocity of the car? Let's talk about it right, starting at this peak right here. Are you saying the car is slowing down through here? I think it's slowing down because what's its speed right here? What's its velocity right here? 0. It stopped. That would correspond to these parts here where it's leveling off, right? Slowing down. Now, what's the car doing right here? It's actually speeding up, right? It's heading back to Bismarck, but isn't it speeding up? See, and sometimes people look at a graph and say, oh, this graph's going down means it's slowing down. No, it's slowing down here because it's headed towards a 0 speed. But now it's going away from a 0 speed, so it's actually getting faster, right? So when the velocity graph's headed to 0 is when it's slowing down. Headed away from 0, it's speeding up. Okay, so there's all kinds of things like that. Again, if you've been in physics, you maybe see some of this a little easier, but it's one of those things we'll talk more and more about. All right. Another thing that I want to mention here. We got a couple more to get through, and then hopefully we'll have some more time. If f prime, if the derivative of a function is simply a plotting of the slopes of that function, couldn't we repeat this over and over? Doesn't this graph have slopes? Couldn't I come to another graph over here and plot the slopes of this graph as y values? The derivative of the derivative. Absolutely. And that is now, we won't do it more than one more time, hardly ever, okay? I mean, so this is about the limit. And we call that f double prime. Just put another prime symbol in there. We'll call that f double prime of x. And that is the derivative of f prime. So if you have f double prime, it's simply the derivative of f prime. Or we will call it the second derivative of f. So you'll hear terms like first derivative and second derivative. So f prime is the first derivative of f. F double prime is the first derivative of f prime. But f double prime is the second derivative of f. Okay? Yes?
What's the practical application for?
Great question. Usually that's not a good question, and I'll say, gosh, I don't know, probably nothing. But that's not true, but usually if I can think of one, you won't buy it anyway. I have this theory, and I know because I was one of these kids, and if I just wanted to bug the teacher and say, when am I ever going to use this? You know, I didn't really care. I didn't want to know when I ever going to use it. I just wanted to bug him. So f double prime, so we'll get to that in a second. So the f double prime is a derivative of f prime. Another way to think of it is it's the rates of f prime. Another way to think of it is the slopes of f prime. Okay? So, in this particular example, let's think about this now. The position function is miles. The rate of change of miles is miles per hour, right? Which is speed, velocity. So that's a great application, right? I mean, we care about how fast the vehicles move. What's the rate of change of velocity? Acceleration. The rate, if your velocity is changing, you're accelerating, right? Either slowing down or speeding up. And what is the units of that? It's miles per hour, the velocity units, divided by the x units. Miles per hour divided by hours. Now, a lot of times you call it miles per hour squared. I think a better way to call it is miles per hour, because that's really what's happening. It's the rate that your miles per hour are changing per hour. Okay? So I'll usually say it that way, but miles per hour squared is the same thing. So, in this particular graph, we could have another graph that would be acceleration, call it A of t. That would be equivalent to what? The derivative of, which one of these up here? A would be the derivative of p prime. It'd also be the derivative of v, right? This is the derivative of these, right? So the derivative of v would be v prime, and I'm out of space over there, so I'll move down here. Or it would be the second derivative of p. It would be the derivative of p prime. The derivative of p prime would be p double prime. Now, and so that is an applicable thing. It is the eastward acceleration. Now, I'm not going to get too far into the physics of this, but there will come a time when we want to make sense of this. Somebody in the other class asked, okay, is a negative acceleration mean it's slowing down? No. People sometimes confuse the term acceleration and deceleration. You won't ever hear me say deceleration. We're just talking about speeding up or slowing down, because I think that just confuses me. Negative, think of it this way. Gravity is a great example of negative acceleration, right? Now, why is it negative? Because it acts in a downward direction, right? Positive, we'd say, is up. Negative is this way. So gravity acts in this direction. If I throw a ball up in the air, gravity is acting on it. What's the ball do? But speed-wise, it slows down, right? Now, why is it slowing down? Because the velocity is positive, upward direction. The acceleration is acting against that, negative direction. So when velocity, so you need both velocity and acceleration to know if it's speeding up or slowing down. So Velocity positive, but the acceleration is working against it, it's going to slow down. But when the ball drops, it speeds up, right? Why? Because the velocity is negative, because it's going in a downward direction, and the force, the acceleration, is acting in that same direction. So if velocity and acceleration have the same sign, they're acting together, the object speeds up. If they have different signs, they're acting against each other, and the object slows down, okay? So speeding up and slowing down are different than just plain old acceleration. Positive acceleration just means the force is acting in a positive direction. Negative acceleration just means it's acting in the negative direction. So in this case, a positive acceleration would be like if we attached a rocket booster to the car and it shot it to the eastward. Or if we turned the rocket around and made it go the other way, if it was being forced to the west, that would be a negative acceleration. Being forced to the east, or step on the gas, I guess you could say. Put it in reverse, and you're facing east, put it in reverse, step on the gas, your accelerating is negative because your force is going in the opposite direction. Okay, I guess you could brake as well. Let's say you did that. Let's say you're putting on the gas, so you're accelerating, going this way, so your acceleration's positive. What happens when you hit the brakes? The acceleration is now going the other way, right? Because your force is now slowing you down. So the force is acting this way, but your car's going this way. And so it slows down. Okay, so that's the best I can do probably for thinking about that. Now, so again, very valid question, why don't we do a third derivative? Because it doesn't really have much of a practical application, so we don't really do much with third derivatives. There is a time when the fourth derivative has an application, and we'll talk about it, but we rarely do anything with it. Okay? There is actually a name for that, though. The derivative of acceleration is jerk. Very good. The rate of change of acceleration is called jerk. And that's about all I know about it, but, you know. So, is that because if you change your acceleration, it jerks you? I don't know, but that is what it's called. Okay? All right, last thing. And this can be a little bit confusing, but we're going to break it down. We're going to break it down and do the best we can here to make sense of it. So if you turn to page 42, I believe. 42, yes. Now, on your way by that, on page 41, there's a problem. It's example 4 that talks about throwing a baseball up in the air at the Metrodome or something, and in Minnesota or something. It talks about the speed and acceleration. It gives you a couple of equations. I only point that out because a couple of your homework problems refer back to that example. So when it says, it says right in the problem, see example 4. So you'll just have to read that example and you can get stuff from that. Okay? All right. So on page 42, there's the box down at the bottom that says the speed limit law. The speed limit law. Okay? Now, we don't do a lot of theory in here, but we do a few theorems in kind of technical jargon because they're fairly important for what they represent. Now, sometimes it's hard to see the importance of them until we get farther into stuff and we use them more. But here's what this one says. If f prime of x is less than or equal to m for all x in the interval a, b. Okay, now the important parts of that are just for all, and then of course this part right here. And we're going to break that down here in a minute. But it just means all the time, in whatever interval you're in of that function, f prime of x is less than or equal to m all the time. Okay? We'll talk more about that in a second. Okay? Then, f of b minus f of a is less than or equal to m times b minus a. for all x in AB. And again, that just means all the time. Now that just looks like a bunch of kind of mumbo jumbo until we start thinking about what it really means. So first we're going to talk about in terms of slope, because we got f prime, and we said that f prime, we can think about it as slopes, we can think about it as speeds, rates of change, okay? So let's first talk about it in terms of slope. So let me draw a little picture over here. Let me put A, let me put B, and we'll just put some kind of function in there, like so. Now, first of all, something we just got in talking about for this last quiz. When you see f of b, you should think what? You see f of b, you should think what? The output at b, right? The y value. That would just be this right up here. Here's f of b, right here. Right? And here's f of a, right here. Okay? So let's just, we got some function, a, b, are the inputs, f of b, f of a are the outputs. Okay. All right, so let's go through and let's interpret in simple person's language what this is saying. F prime is what? What do we think of when we read f prime? Slope or rate of change? Derivative. Let's do slope right now. So this is slope. So this is saying that the slopes of f are always littler or equal to, right? I mean, that's what it says, less than, right? But simple language, right? Littler. So the slopes are littler or equal to m. So what could we call m? If m is just a number, okay, m's a number. M's a number that the slopes are always littler than or maybe equal to. How about max slope? Perfect. Love it. Wouldn't m be the max slope that this graph ever has? The steepest that this graph ever is. That's what m is. M is the steepest this graph ever is. So we know m is the steepest this graph ever is. Okay, so if m is the steepest, now why didn't they just say that in words? Well, sometimes you need math lingo to say things, but quite honestly, when you're saying complicated things, if you understand the math lingo, it actually simplifies it. I mean, I know it's hard to think that that's true, but it actually does. Okay? Complicated story problems, if we can get them written into math lingo, we can solve them, because that's why we learned all that algebra and all that stuff. Right? If we can get it into the math lingo. Okay, so here we go. What did we say f of b was? That's this y value. F of a is this y value. What's this y value minus this y value? Now remember, we're talking about slopes. What's this minus this? It'd be the difference between the two, be the distance between those two. Remember, we're talking about slopes. No, but it's just the y minus y, right? It's just the y minus y. What do we call that? What? Rise, right? Rise over run? I mean, yeah, I know. You guys were all saying good stuff. Like I was trying you to hit this magic thing that you had no idea what I was trying to get you to say. But, right, it's rise. Because we're talking about slopes. Slopes are rise over run. If you take f of b minus f of a, the top part, that's just the rise. Okay, so this is the rise. Okay? And m, we already said, is the max slope. And what's b minus a? Ah, there you go, right? Now you're thinking along what I'm thinking, right? So b minus a is the run. So let's think about this. So what are we saying? Rise is equal to slope, rise over run, times run. Oh, that makes sense, right? Run would cancel, I get it. But this was actually max rise over run, wasn't it? So what we have is the rise, and this would be less than or equal to, right? What we have here is the rise is less than or equal to the max rise over run times run. Well, that's max rise, right? So the rise is less than or equal to the max rise. Oh, that makes sense, right? So big deal. What did that just say? Here's what it said. So if we had to put this into layman's terms, it would be this. If we know the steepest the slope ever is, the biggest the slope ever is. We know the steepest the graph ever is. Then we know for some run, that's from A to B, we can tell how big the rise is. That's kind of common sense, isn't it? If we know the steepest the slope will ever be, then if we know for a certain run, we'll know the most it could go up. Okay? Now, let's put that into rate terms. Instead of slope, let's talk about speed. And instead of rise, if those were miles on the y-axis, what would f of b minus f of a be? Distance traveled, right? And what would b minus a be if that was hours on the bottom? Time traveled, hours traveled, right? Time traveled. Yeah. So this would be, if we know the max speed, if we know the fastest we ever went. See, and you got to put this in context. In algebra class, we always talk about constant speeds. If you went 60 miles an hour for 2 hours, well, that's easy. But we're talking about changing speeds, right? We're talking about constantly changing speeds. So now that's a whole different ballgame, right? If you're changing speeds, it's a lot harder to tell how far you went if you're always changing speeds. You see what I mean? So that's why there's some value in this. So what this is saying is if you know the fastest you ever went, because that's pretty easy to find out. Knowing all the speeds might be hard, but knowing the fastest you ever went, if you know the fastest you ever went, then the distance you traveled has to be less than or equal to the speed times the, what was this? Time, right? Distance equals rate times time. The distance you traveled has to be less than or equal to your max speed times your time. So it would sound like this. If I know the fastest I ever went is 60 miles an hour, and I went for 2 hours, what do I know? The farthest you went is 120 miles. See, in Algebra 1 class, you'd say, well, if you went 60 miles an hour for 2 hours, you went 120 miles, right? Well, you went at constant speed. What we're saying is if you know the fastest you went was 60 miles an hour, then over 2 hours, the farthest you went was 120 miles, okay? So, yeah, it's kind of common sense, but it's, that's what it means in that lingo. So what would a homework problem look like? You might be interested in that. So let's do one. So using the speed limit law, oops. Okay, so a homework problem looks something like this. F prime of x is less than or equal to 2 for all x, that'll be all that stuff, blah, 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 in, some interval, whatever. Okay, a lot of that stuff you see there isn't a big deal. And they also tell you that f of 2 is equal to 4. And they'll write the question a lot of different ways, but one way it could be written would be write a bound for f of 5. When we say a bound, like we were just saying the most we could have went was 120 miles an hour. So the bound there would be less than or equal to 120. Right? That's what we're talking about. Okay? So, all right, now I would suggest not trying to use the speed limit law as a formula that you plug into. I don't think that usually works very well. I think you want to understand what it's saying. So what I would do if I was doing this problem is draw a graph. Okay? And I would draw a graph of f. Let's label it here so we understand what we're doing. So what information was I given that I can put on this graph? The 0.24, right? So I know f's, so that's like a starting point. If this was a speed problem, I'm telling you where I start, okay? And where am I going? To an x value of 5. What I want to know is where could the f graph possibly go, and where would it could it possibly end up at f of 5? Well, I would do it like this. If we're going to go over 3, now what do we know about the slope? It's at most 2. So if we're going to go over 3 and the slope's at most 2, what do you know? You could go up 6. The most we could go up is 6. Rise over run has to be 2. So 6 over 3 would be 2. So we could go up as high as 6, which would put us at what, 10? Right? So we could have, this graph could have went as high as 10, but could this graph have went down? Yeah. I mean, it could have went anywhere, but it could not have went above 6. So what would you say? F of 5 is less than or equal to 10, right? 6 is how much it could go up, but it already was at 4, right? It was already at 4. It could go up 6. So the most it could be is at 10. Now, another thing they might do to you is they might add this to it. They might have said, well, the slope is between negative 2 and 2. So now it could, if it went over 3, it could have went up 6, or it could have went down 6, right? So now that function's got to be somewhere between negative 2 and 10, right? You could use that notation, or you could use the notation you can. Okay? All right. So that's not that hard. I mean, really, when you think about it, it's really just saying, hey, if you know the max slope, and you know you want to go over this far, how much can you go up or down? I mean, that's really what it's saying. So reading that notation, that's called the speed limit law, right? If you know how fast you're going, then you should know something about how far you travel. That's really in the nutshell what it's saying. Okay. So, and in function terms, it says if you know something about the slopes of f, then you know something about the y value. That's kind of what the speed limit law is. Okay, 1.4 homework is your assignment for tomorrow. This one's important. I mean, this one's got a lot of this new notation, understanding this stuff. I'll be here early in the morning if anybody needs to come in. Like I said, I will be having to leave class a little early tomorrow. We'll try to answer questions on homework as best we can. The new stuff tomorrow will be a lot of this zooming in and actually doing some calculating of slopes. We'll literally be getting some points and doing slope calculations. But tonight's homework doesn't really have that. It's more about this notation, stuff like that. Okay? And we'll continue to flesh this out and work on this stuff over the next 4 or 5 days. Okay? We got about 12 minutes. You can get a little bit done maybe, but
Thank you, sure.
For when we were at state.
oh yeah, that's right. I never did see that. That was 1.2.
Yeah, I think so.
I thought it was Mark out there. And I thought, God, he's over there. Is she over there yet? I forgot. I got to leave early today too.
It's alright, you're there, your boss.
Oops. Yeah, I got to get class ended. Yeah, you can take the hats off. That's fine.